Welcome, everyone. We're glad you're here. My name is Aaron Whedon. I work for the Shodor Education Foundation, and we're part of the education program of the National Science Foundation's EXCEED project, which stands for the Extreme Science and Engineering Discovery Environment. And here at Shodor, we also run the National Computational Science Institute. And we're excited to welcome you to this webinar on computational thinking across the curriculum. Before we get started into the main content of the webinar, I wanted to read a couple slides to you. So I'm going to share my screen. So EXCEED has an external code of conduct, which represents our commitment to providing an inclusive and harassment-free environment in all interactions, regardless of race, age, ethnicity, national origin, language, gender identity, sexual orientation, disability, physical appearance, political views, military service, health status, or religion. And this code of conduct extends to all EXCEED-sponsored events, services, and interactions, including today's webinar. The Code of Conduct has a website at exceed.org/code of conduct. The organizers today are Bob Panoff and myself. And you can also contact any of the EXCEED ombudspersons. There's also an anonymous reporting form available. And in line with the Code of Conduct, EXCEED is also committed to providing events that foster inclusion and show respect for all. And this applies not only to how we interact during the event, it's also applying to the materials and presentation. And it's not EXCEED's position to use, condone, or promote offensive terminology. EXCEED instructors strive to keep inclusive language at the forefront. In the event that we have included inappropriate materials, either verbal or written, please let us know at terminology@exceed.org. And while EXCEED has no control over external third-party documentation, we are taking steps to effect change by contacting the relevant organizations. And we hope this will be addressed by all third parties soon. So if you have any terminology concerns about the following presentation or materials we want to know, please contact the Terminology Task Force at terminology@exceed.org. Okay, so I'm going to stop sharing now and turn it over to Dr. Bob Panoff, who's going to be leading us in today's webinar. So over to you, Bob.
Thank you very much. For context, this is the second of two very similar presentations. I'm using the same outline, but the examples depend upon the attendees, and the questions you ask and the comments that you make. I am going to have a slight difference in this workshop compared to the one 2 weeks ago, in that people asked me to spend a little bit more time mentioning items that impact parallel thinking and parallel computing. So the extreme science and engineering environment of EXCEED typically ends up on very large machines with many processors, massively parallel multi-processing units, but we have to start somewhere. And this webinar is to sort of describe successful methods of getting people on the ramp towards high-performance computing. High-performance computing starts with good computing. So after this workshop, there will be 3 follow-up. After this webinar, there'll be 3 workshops in June, each one of which will run over 2 days for a half a day each day, Tuesday and Wednesday for each of 3 weeks. In the first of those workshops, we'll talk about web resources and spreadsheets, trying to get students to understand that without necessarily requiring a large amount of programming, you can build a model. And we'll do that from that standpoint. There's a tremendous amount of computational thinking that can be taught using Excel or Google Sheets as a sandbox. The next workshop will be on system thinking, system modeling, system dynamics. It's a very large area of model construction and model thinking. And the third will be on agent thinking, agent modeling, agent dynamics. So I'm going to share my screen. This is the URL that we'll be using. You can follow along. You can watch my presentation. You can click on things. If you click too far ahead and you get lost, just come back and go to the document that Aaron posted in the chat window and catch up the best you can. So when I talk about computational thinking across the curriculum, what I mean is that except for the semantics, many of the computational models and tools are applicable in physics, chemistry, biology, psychology, geology, economics. And it's a matter of understanding the underlying basic computation that enables the thinking. If the computation gets in the way of the thinking, we haven't made any progress. And the idea is that this will be done primarily in an inquiry-based approach, where we'll be asking driving questions, we'll be asking questions about observations, and we'll be sort of trying to conduct what we call science at the speed of right. If you're doing it on a computer, it doesn't do any good to be doing it fast if you have no reason to believe the answer. So we'll talk about that as we're going forward. For many years now, I've talked about the two breathing modes of computational science or computational thinking. The first is computational science education, in which we're using tools and models that have been thoroughly vetted. They have gone through a process of verification and validation. We're using a computational environment to teach the content of math and science education. About 80% of the use of computing is in this vein, and we'll give some examples across different disciplines. But this is not to minimize the need for programming, but just to point out the fact that most of the uses of computation in the sciences, in mathematics, in education, are using tools that have already been built, and the students need to learn to run and interpret the models, not necessarily build them. On the other hand, the other breathing mode is computational science education, which is in fact teaching people how to build the model, how to conduct the verification and validation, how to build the code, how to look at multiple algorithms, how to map science onto different architectures. So as we're coming through here, we have this idea of most of what we're going to do today is talking about computational science education, that the thinking that goes into science and learning science will be enhanced by the use of computational tools. Now, with computation, experiment, and theory coming together to form a model, the matching also has to be between the architecture, the application, and the algorithm. And there are different computer architectures. There are different algorithms that run better on some architectures than others. There's different applications that run with some algorithms and better than others. A very simple example of this could be using a digital computer, and I'll distract you here. Using a digital computer, counting, if this is the architecture, then we could have an algorithm that maps onto an application. And with a 10-fingered computer, an application that's very natural is multiplying by 9. The algorithm is starting from the left, you count over and drop the finger that you want to multiply 9 by, and then read the answers to the left and to the right of that finger. So 9 times 3 is 27. 9 times 2 is 18. 9 times 8 is 72. So you have this idea of the match between the application multiplied by 9 the architecture, your 10 fingers, and the algorithm, which is drop the finger, read the answer. Now, if you had a system which only had a 9-fingered system, if you could use 10 fingers to multiply by 9, it may or may not be obvious to you that you could use a 9-fingered system to multiply by 8. Let's see if it works. 8 times 4, 1, 2, 3, 4, gives you 3, 5. You say, wait a minute, I thought 8 times 4 was 32. It is, but 3, 5 is a numeral in base 9. 3 times 9 is 27, plus 5 is 32. So if you change the architecture, you may have to change the algorithm. You may have to change the applications that run well on it. For the past 30 years, as the National Science Foundation and the Department of Energy have funded different supercomputers, as the architectures have changed, people have found that they sometimes had to make radical changes to their code in order to get the maximal performance on the new architecture. So keep in mind that part of the computational thinking is how do you match the application, the algorithm, and the architecture to support the investigation of a particular model. And that's something that we're looking at as we're going through. Now, all of this is based upon what's called the universal theory of everything. And if you click on the model, you will get the universal theory of everything, which is that the right answer is the wrong answer plus corrections. And a lot of times you just have to start with a simplified model, which is admittedly the wrong answer. And then you add embellishments to that. And one of the corrections that may have to be made is the fact that you're doing the calculations numerically with finite resolution, truncation, and round-off contributing to the uncertainty that might otherwise be in the model. But we can make amends for that with the various corrections, or we can control things with different changes. Sometimes by changing the algorithm, you can change the impact of some of these computational errors, and you can remove certain instabilities. But that's, again, part of the whole computational thinking that we're trying to push ahead. So computational thinking allows any explorer to manipulate a dynamic computational model with sufficient power to recompute and revisualize the model. So our goal is a dynamic, visual, interactive model. It's a matter of putting the control of the model in the hands of the user. And again, for what we're going to talk about today, we're not going to necessarily talk about what you have to do to program that to happen, but to take advantage of the fact that someone else has already built the model or built the tool. Let me give you a simple example of that coming from the Interactivate set of tools from Shodor. Interactivate was originally created to provide content for an experiment that was using the Department of Defense schools on the military bases around the world and around the country, where children of soldiers and sailors and airmen were given the opportunity to spend up to an hour or more per week on a computer. This was back before computers were ubiquitous. But back in the late 90s, early 2000s, computers were put in all these schools, and the teacher said, what are we going to use these computers to do? And we were one of several groups that built a lot of curriculum to show them the effective power of interactive, dynamic, and visual computing. So there's a lot of controversy these days over the SAT. Some claim it's not culturally relevant, and some claims that it's not even a good predictor of college performance. And if you took the data from 173 students, these are the math SAT scores, the mean of those students is about 500, which is to be expected. 500 is halfway between 200, the lowest score, and 800, the highest score. And every school in the country has an average of about 500. Now, one way to represent all of that data to see if there's a pattern, because modern science and math is all about pattern recognition and characterization, not merely symbol manipulation. So we want to look for a pattern in the data. And a histogram is a data tool, comes out of years of data science and ways of representing large amounts of data by seeing if there are clusters in that data. But a lot of the students find making the histogram to be tedious and repetitious. So by having a computational tool where you have all of your data in your tool that's entered in, and then by grabbing the width of the interval, you can change the representation by changing the width and representing the data, changing the width and representing the data, changing the width and representing the data. And one thing is clear is that it's easy to show that one representation is that this data is center-peaked, even-tailed, and continuous. It's just an example of an almost normal distribution. And people say, well, that's not going to help you very much for picking which students should go to college, which one shouldn't. Everybody's the same with a few better and a few not as good. But if you continue your analysis at different interval widths, it's not hard to come up with a wide range of values in which at 450, 550, 650, and 750, you get local maximum. And it turns out that this large data set is really overlapping data sets. And by further analyzing which questions students got right or wrong, it's been able to be shown that the students in the 450 range have basic arithmetic. In the 550 range, these are students that can solve one equation and one unknown. In the 650 range, these students can solve two equations and two unknowns. And at 750, these are students that can do all of that on a Saturday morning over a 3-hour period without getting tired, without getting frustrated, without falling asleep, without spending too much time on one problem or another. And so the representation is determined from the representation of the data. And you could do that with other data sets as well. But the tool, once you put in the data, you can cut and paste data into this. Once the tool does that, then you can use the power of the computation to free up your mind to read and interpret the data rather than construct the histogram. So multiple representations help you form multiple representations. And this is why some computing companies have referred to computing as a thought amplifier. One reason for making it visual to get a really second sense involved in seeing the pattern of the data comes from another software company that said, we make it visual because you cannot memorize understanding. So computational thinking supports an authentic view of science. It allows you to look at what science is. And a lot of people have this caricature that everything is hypothesis driven. And I would argue, no, it isn't. A tremendous amount of science is observational. People collecting observations to give something as data. Data comes from the Latin to be given. The question is, what have you been given? Well, many times it's the observations of others. Tycho Brahe was a brilliant scientist, but he didn't have his own theories. What he had was the observations he made night after night, recording the positions of the stars. But if you simplify any model you have of science, it should come down to three basic parts that are interchangeable and are actually looped through. And that is expectation, observation, and reflection. Oftentimes we start with an observation, we think about it, we reflect on it, and it causes us to expect to see something, and we go back out and look for it. But this idea of expectation, observation, and reflection can also complicate things computationally. If students have the wrong expectation about what a computer is going to do for them and don't understand it as a tool that's under their control, then this can be something that can lead to confusion later on. Let me give you a simple example of expectation and maybe how we have to change students' expectations with respect to computation. So if I gave this simple expression, 3 + 2 × 6, what would you hope or what would you expect your students would be able to evaluate this expression? What would you hope they would get as the result of evaluating this expression? And when I ask these kind of questions, I'm trying not to be too rhetorical. Just hit your space bar, shout out your answer. Let's make this as interactive as we can. Who would like to propose a value for this expression?
We're getting a lot of 15s in the chat.
In the chat one, okay. Now, perhaps you're saying 15 because you are expecting that order of operations, that if you added 3 + 2 × 6, the 2 × 6 would be done first to give you 12, and then you would add 3. And there are a lot of students who expect that any computer, especially a modern computer, because that's what they get on their little hand calculator. If you type it in 3 + 2 × 6, they get 15. That's not necessarily the case with computers. Now, what I'm going to show you here is a calculator that's been ported from Windows. This is the Windows calculator. I would ask that somebody who is watching this webinar on a Windows machine go to your calculator under all programs, and you should have the standard mode. And this is how the Windows calculator comes up. And if you type in 3 + 2 × 6, you get 30, not 15. Because what Microsoft means by standard is not the NCTM, National Councils of Teachers of Mathematics standard. It's not the National Science Standard. This is a standard checkbook calculator. And they assume that that's the calculator people want to come up. You'll also notice that there are no parentheses that would allow you to isolate it. You would have to do the calculation in a different order to get a 15. If you did 6 × 2 + 3, you could get 15. But you, the thinking human being, have to recognize that the calculator doesn't do order of operations on its own. You have to provide that extra piece of convention. Order of operations is a convention, it's not a theorem. Now, if you were to change from standard to scientific, I might ask you, what do you notice about science compared to just a standard calculator? Do you notice it's got a lot more buttons and it's a lot more complicated? But here's something else that the Windows calculator does in this mode, and that is if you type in 3 + 2 × 6, it's now doing order of operations. And that's unexpected for a lot of students. They want to use the standard calculator because it's simpler, but the standard calculator doesn't provide order of operations. You yourself have to do that. So this is kind of, one example of things that are going on. And it's going to be different for different computing environments. We'll show you a really simple example here. If I go to Excel, I'm going to share my Excel screen with you. You should be able to see my Excel workbook here. If I came over here and you say, how does this, what are the expectations that you would expect on a computer? And some of the expectations that are unexpected is that certain rules that you've learned since you were a child, the commutative law, the distributive law, the associative law, don't necessarily maintain their integrity on a numerical environment. Algebraically, the commutative, associative, and distributive laws hold. Numerically, there could be issues. So again, using your space bar, if I gave you a simple calculation like 3/6 minus 3/6, so I'm going to take 3/6 and subtract them from 3/6. What would you expect to get?
We're seeing 0 in the chat.
And you get 0. And then you could ask yourself, is that just formatting or is that really 0? And you could say, if this is really equal to 0, I want you to write 0. Otherwise, I want you to write not 0. I forgot my quote. And it says it's 0. Now, if I come over here and if I take this expression, and this is not the distributive law, this is putting the entire arithmetic in one set of parentheses. I hope you wouldn't expect, because most people wouldn't, depending on how much you've had on numerical computing, most people would expect to get the exact same answer in Excel because they think that's how Excel works. And yet, if you calculate it, it's clearly not 0. This is kind of Microsoft shorthand for don't lie to me. If we used English to describe these parts, 3/6 is 1/2, which is a power of 2, which is exactly 1/2. It's 1/2. But 1/6 is not a power of 2, even though the denominator is even. And so 1/6 is actually approximated. It's not really 1/6 because there's a finite number of digits, and at some point you have to stop. And the question is this rounded or is this truncated? If the computer calculates 1/6, do you see that it's rounded or truncated? Well, what does it look like? Does it look like it's been rounded up? But that can't be the case, and that's use some computational thinking. Go back over here, and I'm going to describe this again in English. According to this representation, this is not 1/6, it's almost 1/6. So this is exactly 3/6 minus almost 1/6 minus almost 1/6 minus almost 1/6. When you do that, you get almost 0, but not 0. But here's the hitch. if this number really is rounded up, that means that the representation on the computer, as it's saying, would be more than a sixth. And if that's the case in English, this would be exactly 3/6 minus more than a sixth, minus more than a sixth, minus more than a sixth. And that should give us what kind of number? Anybody want to chime in?
Negative in the chat.
Negative. And yet it's positive. So that's one of the unexpected results, that numbers are formatted in a computational world to make them look like they're base 10 when in fact they're stored as ones and zeros. And Microsoft did some marketing and found out that people expected 1/6 to look like it was rounded when you got to that last digit. It would look funny to them to just truncate. But so that means that there's a formatting subroutine that takes the ones and zeros and converts them into decimal and puts them out here. But order of operations, the parentheses, exponentiation, multiply, divide, add or subtract, those are conventions, not theorems. Let me give you another example before we go away for a second. If I had -4 squared, if you do the exponentiation first, what would you expect -4 squared would give you? Well, let me just show you that, to the exception of every other software I can find, Excel tells you that it's +16. All right, now let's back up here. And I want to see if I still have this up. I'm just going to my terminal. And do you see my Python window? And if I type 3/6 minus 1/6 minus 1/6 minus 1/6, without any parentheses, this really is the result of taking 3/6, which is exactly a half, and subtracting 3/6. And do you notice that in this particular case, the representation does not in fact round it, it shows the truncated number that's in Python. So depending on how you're doing it. Now, if I ask the question, what is -4 squared? It says it's -16. So already you can see that there are differences between computing environments, and the requirement of the human is to provide the thinking that says, if I use Excel, what do I have to keep in mind? If I use Python, what do I keep in mind? If I'm writing Java, JavaScript, Fortran, C, C star, C++, what are the differences? What should I expect to get when I do even a simple numerical calculation, let alone when I sum the gravitational force of hundreds of thousands of stars in a galaxy? So these are the little things, and they're not hard, but they are required to sort of change the expectations some students may have that all of this will be taken care of and it's already been solved and everybody agrees on how to do these calculations. Every computational environment is going to be different. So let me get back to my sharing of the screen. So there are different kinds of things that are going on. I want to spend a few minutes in this first hour talking about a few examples of different ways that you can stimulate thinking in your students through constructing exercises along an inquiry approach. rather than just a worksheet or hypothesis-driven approach to math or science. To do that, we need to think about these models of inquiry. And this is something where we've tried to expand expectation, observation, and reflection into a series of questions. What can I observe and what do I observe? What is observable without help, or what is observable with help? And is what you observe changed by the help? I mean, if you want to look in a telescope or a microscope or a computer, how is that changing what you're actually observing? You can ask, are your observations accurately recorded and honestly reported? I can't tell you how many papers have been withdrawn, and the rate of withdrawal in medical journals it's just growing exponentially because people feel a rush to publish. And in fact, sometimes their data is not accurately recorded and it's not honestly reported. And then the question is, what can be concluded or what could be said that's consistent? The difference between science and math at one level is that science has very few theorems. Even the laws are really patterns of observation. And as we get new observations, sometimes those laws change. But what you can say is, given the data that has been given, what can you say that's consistent with that data? What can you compare that to what others have done? And why should you care that that's done at all? Now, consistent with this computational thinking, I want to talk a little bit about our friend Google. And the first thing I'll do is I'll type in the same expression that we had before, 3 + 2 × 6. And I don't know if you can tell, but when you do that, well, that didn't work. I just erased, there it is. That not only does Google look at this 3 + 2 × 6, but instead of giving you the 25 trillion web pages, it provides a calculator and does the calculation for you. And it includes parentheses around the 2 × 6. Can anybody hit their space bar and shout out why you think, what does the 2 × 6 in parentheses communicate?
The order of operations.
Order of operations. So that's telling you why it's getting 15 and not 30. And you also get this entire calculator that comes up. Now, I don't know if you've had the experience in your class when you get your students to type something in. Sometimes they think you mean it literally. So if I said, class, I want you to type in 3 + 2 × 6. I misspelled 2. Well, Google understands English anyway. What numerals in English represent those numbers? So we could ask Google, what is -4 squared? And Google says it's -16, just like Python, not like Excel. If you had done this thousands of years ago, the calculation might look, even though I don't think they had the same symbols for plus and times. What if you did capital III plus II times VI? Those are Roman numerals, and it may or may not be expected, but the answer is XV. 1 group of 10 and 5 groups of 1. So we're getting those things that are there. And there are other parts of Google Let's see if we can. Now, there's all sorts of Easter eggs in Google. If you were to type in the word recursion, I don't know if you've seen this. It comes back and says, did you mean recursion? And if you click on recursion, it says, did you mean recursion? I don't know, some of us think that's funny. Or if you typed in the word askew, do you notice the entire page is now showing you what it means to be askew? So, I mean, Google could be your friend, or it might not be. If you were to ask Google other questions, one of the things that's coming on is the expectation of things, and we'll come back to this in a little bit. But what I want to do here is talk about this idea that in computational thinking, how you compute something and that you compute something depends upon students' expectations. And the results can be very different depending on it. And every time I've done this part of the presentation, I've gotten different results, so I don't know what to expect. But what I'm going to need is for one of you to volunteer to verbally perform a simple instruction that I'll give you so that everybody in the class can hear you. So who would like to be our volunteer? Can somebody unmute and identify yourself?
Sure, this is Nick.
Okay, Nick, can you count from 10 to 1 backwards?
I think I can.
Okay,
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
good. Now, what did you mean by backwards?
Going from 10 to 1 by 1 increment.
Okay, but if I had asked you, Nick, can you count from 1 to 10 backwards? What would it have sounded like?
I'm not sure.
Well, my guess is if I asked you to count from 1 to 10 backwards, you would have started at 10 and ended up at 1.
Oh, I see. So from 1 to 10 backwards, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Right, that's why I asked you, what did you mean by backwards? And I think what you meant by backwards is exclamation point, yes, really, really, really count from 10 to 1.
Mhm.
But in other contexts, the word backwards actually changes the algorithm. And there's
That's
lots of ways to count from 10 to 1 backwards. What would be another way?
10, 8, 6, 4, 2.
You could count by twos. Right? But again, if you want to have the word backwards have a meaning, what would be different meanings of backwards that would allow you to have, if someone said count from 10 to 1 backwards, you already gave me one example where backwards means yes, really count from 10 to 1. You gave me another one where 10 to 1 backwards starts at 1 and ends at 10. But somebody could come up and say net, enin, tegef, nevis, zif, evif, roof, ir, eno. No, I skipped 2, out, eno. So each number from 10 to 1 is pronounced backwards. But the big part here is that there is an expectation that when you're describing an algorithm or you're describing a procedure in science, that sometimes what happens is the words become ambiguous and they're not necessarily as clear as we would like them to be. And computationally, things like order of operations remove some of the ambiguity, but not all of it. One of the things that's good is that some algorithms are interchangeable, and the fact that you keep getting the same answer no matter how you do it gives you some confidence in what you're doing it and how you're doing it. But this expectation, observation, and reflection is part of this whole getting the students to expect, what do they expect to get when they do a calculation on a computer or run a model on a computer What do they observe, and trying to provoke them to make very careful observations that can be accurately recorded and honestly reported. And then to also reflect on it, to make sure that they're thinking about what they're doing. Sometimes we just have the expectation and the instruction, but the students don't really have the experience that you have or that I have to figure out what is it that they're supposed to be doing. Why are they doing it? I'll give you an example from one of my recovered memories. When I was a small child, 3 or 4 years old, I was about to cross the street, and because I grew up in America, there was a 3-word instruction that was ringing in my ear because my mother had told me over and over that I should do something before I cross the street. Does anybody want to share what your parents told you to do before you cross the street?
Look to your left.
Okay, well, look to your left is one way, but that's only part of it.
Stop, look to your left, make sure there's no cars coming.
Well, that's a lot more detailed than mine. When I grew up, it was simply look both ways because the car could be coming from either direction. If you only look to the left, you could be going and then the car from the right could hit you. But most kids that I've run into have this experience that they were told to look both ways before you cross the street. That was the totality of the instruction. And so as a 3 or 4-year-old kid, I started going, I looked one way, I looked the other way. I stepped into the street. My mother jerked me back, said, "Robbie, what are you doing?" And I said, "I'm crossing the street." "Didn't I tell you to look both ways?" "I did." "Didn't you see that car coming?" And that's where the flaw in the instruction comes in. Yeah, I saw the car. What about it? You know, why would you look both ways? And my thought was, if you can see the car can see you. And what car is going to hit a little kid if it sees him? But you're responsible to make sure the car sees you by looking both ways. Now, the reason why I think that other thing is a 30-year recovered memory. When I came out of anesthesia from one of several surgeries, I remembered that when my father would take a picture with the camera, and I mean the camera. In our house, there was one camera. It's not like today where everybody's got a cell phone with a camera. There was one camera in my house. It was my father's camera, and nobody touched my father's camera. But what he always said before he took a picture of the family was, if you can see the camera can see you, because that means there's no obstruction between you and the lens. And I'm thinking that's what I must have been thinking as a 3 or 4-year-old kid. If you can see the car can see you, because there's no. But without the extra instruction, there can be still some problems with how we describe things. Let's go back and do a simple example. Again, using the arithmetic to do this. If we had the number 8 divided by, wait a minute. Dot, dash, dot, divided by 2 times 2 plus 2. If we did order of operations, can somebody give me a simple statement of what you mean by order of operations?
Some
Well,
operations take precedence, and then if we have an operation that has same precedent or multiple operations with same precedence, we operate from left to right.
All right. So this is the part that when I looked in lots of elementary and middle school math books is left out of many things. What they do is they say parentheses, exponentiation, multiplier, divide, add or subtract. But they don't mention this left to right part of it. And that's caused a tremendous amount of angst on the internet, because if you say 2 plus 2 is 4, 2 times 4 is 8, 8 divided by 8 is 1, as opposed to 2 + 2 is 4. And then you go left to right. 8 divided by 2 is 4. 4 times 4 is 16. So do you get 1 or do you get 16? Without this extra part here, and again, I've been working with a lot of middle school teachers in North Carolina. They don't include the left to right instruction in the earlier grades. That's somehow reserved for later grades, if at all. And the result is that there's still some ambiguity that can be in there. So, you know, as you're sort of going through there, there's different things that can come up. The other part of the ambiguity and where the thinking has to be in there is asking the question, how do you know if it's right? And if we go back to our friend Google, I want to do a simple and that is, suppose you wanted to ask the question, which has more mass, Earth or Mars? And this has come up several times because the Americans and Europe and China are all landing Mars landers. And we've had an experience over the last 20 years of miscalculating the quantities needed to land a lander safely. But what if you wanted to know, as you're testing something on Earth and then it's going to be operating on Mars, what's the effect of the mass? You might want to understand which is more mass, the mass of the Earth or the mass of Mars. Does anybody have a idea or want to take a guess? Well, how would you tell? Is there a simple calculation that you could do that would allow you to figure out which one it is? So Earth has more mass. Earth has more mass. Well, what if you calculated the ratio of the mass of the Earth to the mass of Mars? And if that ratio was greater than 1, you would know that the mass of the Earth was bigger. If that ratio was less than 1, you would know the mass of Mars is bigger. But for those of you in the chat window that said it was Earth, let me ask you a second question. If it is Earth, is it 1? Is it about the same, but just a little bit bigger? Is it twice as big, 5 times as big, 10 times as big, 20, 50, 100? Well, we could answer that with the same question by calculating this ratio. And I want to use this to demonstrate Google's feature that's known as information algebra. I can use that calculator on Google to calculate the ratio of the mass of the Earth to the mass of Mars. But if I were to do that, what would I need to know to do that calculation? Well, I'm going to jump to the answer, and the answer is you need to know how to type. Because if you type in mass of the Earth divided by the mass of Mars, Google goes out and finds a value for the mass of the Earth. It goes out and finds the value of the mass of Mars, takes the ratio and gives you the answer. Now, normally when I do this with middle school or high school teachers, they'll often say, well, you have to know the mass of the Earth and you have to know the mass of Mars to calculate the ratio. Well, in information algebra, the mass of the Earth is a variable that's filled in by Google. The question I ask is, how do you know if it's right? And that's a big thinking question. If I just looked up the mass of Mars, it would tell me that it's 6.39 times 10 to the 23 kilograms. If I said the mass of the Earth it would say that it's about 5.972 times 10 to the 24th kilograms. But if I came over here in Google, what reason do you have to believe that this number is the right number? And the question is, well, you want to look at the source. And Google in a box on the right side gives you the source. And unfortunately, what does it say the source is? Wikipedia. But if you click on Wikipedia and you go down and look at all the properties, instead of 6.39, it says that it's 6.4171. And then it gives you a reference. This is not kilograms to the 8th power, but it gives you a reference which turns out not to have the mass of Mars in it, but it gives you the information you need that you could calculate it. But there is something from NASA called the Mars fact sheet, which has yet another number. So Google says it's 6.39. Wikipedia says it's 6.417. And NASA says it's 6.4185. So if you needed to know the mass of Mars, maybe this isn't the best way to do that. So, I mean, there's other things that come in there that as you're trying to figure out what's happening and how it's happening. If you wanted to do the mass of the Earth, you could take Google's word for it, or you could build a model and use the computation in the model to see if you could figure out roughly what the calculation would be. Let's do that, and then we'll take a short break. So when you're talking about a simple calculation, you start with a model of the Earth. And the first part of the model, we're going to combine 4 things that are wrong, but it's going to be a model. The first part of the model is that the Earth is a perfect sphere. It's not, but it's a model. The second is that the Earth is made up of a uniform substance across the entire interior of the Earth, and we call that Earth. That's not true. There are higher and lower density materials, water, sand, dirt, granite. But as a model, we'll assume the Earth is uniform. So we have a uniform sphere of a known radius. And that radius is the same everywhere because it's a perfect sphere. And then we can do an experiment ourselves on Earth. We take an object, let's say this pen, and time how long it takes to hit my hand, and use that to actually calculate the value of the local gravitational attraction, the gravitational acceleration. And that's equal to this gravitational constant, the big G that makes all the units come out right, times the mass of the Earth, times the same mass that's followed, divided by the radius of the Earth squared. And if we cancel the mass on both sides, divide by the gravitational constant, and multiply by the radius of the Earth squared, we've isolated the unknown, and we can calculate the mass of the Earth if we know the local gravitational attraction. And we assume this perfectly spherical uniform density model. So if we were to do that, I'm going to use as an approximation 9.8 meters per second squared as the value of the gravitational attraction. And I'm going to multiply that by the radius of the Earth squared and I'm going to divide all of that by the gravitational constant. Now, Google is telling you that the mass of the Earth is 5.972. If we use a perfectly spherical model, which is wrong, of uniform density, which is wrong, of known radius, which we don't know, but we'd have to look it up. Google would give us that calculation as 5.973 instead of 5.972. You can see where the fact that it's a model, it may not give you the same answer as the best answer NASA would give you. But it is an important part of computational thinking that you ask the question, how do I know if it's right? And notice that this is in kilograms. Now, an interesting fluke is if I replace this 9.8 meters per second squared by little g, watch what happens to the answer. Because I don't have the meters per second squared unit explicitly there, and then it comes up and takes kilograms and takes the g of the abbreviation kilograms and squares it because it had that little g out in front, you get complete nonsense, right? But you have to be thinking about these things. If you're going to use a computational tool, you, the thinking human being, has to use it intelligently. And as a result, you can get some good results, but you have to be thinking in order to do that. We've been at this about an hour. What I'd like to do is to take a short, let's say, 7-minute break. We timed it last time. That seemed to be enough time. And in the process of doing that, we'll come back and we'll look at some examples of models across the curriculum. We'll do something with math and art. We'll do something from astronomy. We'll do something with nanomaterials. We'll do something with rabbits and wolves. And we'll sort of see how things can be analogous if you remove the semantics, and how one model in one area might apply to something else in another area. So are there any questions or comments or concerns for what we've done so far?
Hi, Wolf. I have just a naive question. You mentioned the 3 workshops coming up in June. Can you post this link in the chat, please?
Okay, I didn't hear that.
It was a question about the 3 workshops in June and the link to it. I can post the link to the Google Doc again. On that Google Doc are links to the 3 registration pages for the June workshops. So give me just a second here.
Okay, so take a look in the chat window and you'll see the link there, and on that link are the 3 workshops in June.
Any other questions before we take the break?
There was a question in the chat window of, can we trust Google? And that's my point exactly. You can trust it to the extent that you can verify and validate the results. The point is that I showed you with the mass of Mars that Google can give you a chain link to one link after another, all of which have different answers. My favorite example of all time is the boiling point of radium. And if you were to search the boiling point of radium and just look at the first 10 links, you'll see 6 different answers. And some of them are not within 50% of each other. We're not talking about a small round-off error. We're talking about numbers that are between 1100 Celsius and 1700 Celsius, with everything in between on somebody's webpage. So that's a very good question. If you get it from Google, how do you know if it's right? That's a very important challenge to your students, that just because they got it from Google doesn't mean that it's right.
There's two questions in the chat back to back about Wolfram Alpha. Basically, do we see the same issues on Wolfram Alpha that we see on Google?
Yes, so let me give you the same example that we've done before. Can you see my Wolfram Alpha page?
Yes.
Now I'm going to type in 3/6 minus 1/6 minus 1/6. I'm sorry. Minus 1/6. And I haven't hit the return. And do you see that it says the answer to that number is 0? Now, if I put a period at the end of the 6, that tells Wolfram Alpha, do the calculation numerically, not symbolically. And do you see immediately you get the fact that numerically you don't get the same answer that you get algebraically? The associative law, if I take these two numbers and associate them together, so even though I'm still subtracting 3/6 from 3/6, depending on how I lump them together, I get a completely different non-zero answer. If I put this number, a 1 here and a 2 there, don't you know from the commutative law that you should get the same answer, A plus B, B plus A? But you get a different answer depending upon whether you subtract the 1/6 first and the 2/6 second. So numerically, you're going to see the same differences. Algebraically, you're going to see the fact that Wolfram Alpha so if I say mass of Mars, it says this is 6.417, even though the NASA sheet had 6.418. Now, one of the things that's interesting about doing this, depending upon how you're doing it, is the sources. So if you click on the sources, this is proof in my mind that Stephen Wolfram has no idea what a primary source is or a secondary source. He says the primary source is what he calls the Wolfram Alpha Knowledge Database. The primary source is Wolfram. He doesn't include a direct measurement. He doesn't include a NASA experiment. So these sources are that he calls primary means, where did Wolfram Alpha look first? That's what Wolfram calls a primary source. And again, you know, the computational thinker in you has to say, wait a minute, when I went to school, that's not what we called a primary source. Primary sources were firsthand measurements or observations. Secondary sources were collections of those data or things that are reported out from people that have used it. But again, Wolfram knows better. Wolfram says this is the answer, and we're telling you we got the answer from ourselves. I don't know if that answers the question. So again, Wolfram Alpha is a powerful tool to use, but it can't be used without you, the thinking human being in control. And sometimes you got to scratch a little bit under the surface to find out that maybe there's some ambiguity, maybe there's some uncertainty into whether or not you take that as the answer, as to the answer that Wolfram gives you. Okay, I promised a break. Let's take a break. Let's come back at 2:20. and we'll go through some specific modeling examples. Okay, it's 2:20 Eastern Time. We're going to talk a little bit about different ways of reasoning and thinking in this particular part of the webinar. Keep in mind that the 2-day workshop on spreadsheets and web tools will go over more of the details, and we'll show you some of what we did in Excel. But treating Excel as a modeling sandbox, you're going to see some examples between now and the end of this webinar today, but we're not going to go in great detail on how those examples were built. We will during the spreadsheet workshop. We'll show you examples of how other ways of doing system modeling and agent modeling can be done. We're not going to go into great details, but we will during the actual workshops on those topics. This is more of a smorgasbord to show you a range of things that could be done. So part of what we want to do in computational thinking is to use multiple paths to solution, multiple representations to talk about representation. And sometimes representation can change your ability to ask or answer a question simply through a modified way of doing computation. So what I'd like to do is to see if we can figure out some of these ideas of different ways of computing something. And the main reason I want to do that is it's the kind of thinking we need to get kids to be thinking in parallel. These different parallel architectures do not yet have high quality parallelizing compilers. A lot of the parallelism is put into the code by hand, and it requires you to rethink the problem. It's not a matter of taking an old code and just trying to get it to run in parallel. It's a matter of taking the science that nature itself is parallel. And we'll talk about that as we go through some different examples. So the first thing I want to talk a little bit about is computational thinking with respect to quantitative reasoning. And I want to talk about different paths to solution. I'm going to keep the example very simple. All right, and the example is, suppose you want to add up all the numbers, all the integers between 1 and 10 inclusive. What would be one way that you could do that? Well, the most obvious is called brute force. And you could just come over here and add the numbers. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 15, 21, 28, 36, 45, 55 would be the sum of all the numbers between 1 and 10. Something that I'm really happy they're teaching at younger grades is grouping. Again, use your space bar to shout out an answer. What if you looked at this as 1 plus 10? What would you get? 2 plus 9, 3 plus 8, 4 plus 7, 5 plus 6. You would get 5 groups of 11, which is an easier calculation than all of the sequential addings, and that would give you 55. Another way you could think about it is if 11 is too hard to think about 10. Let's see if we can find 10s. Well, here's a 10. 9 plus 1 is a 10. 2 plus 8 is a 10. 7 plus 3 is a 10. And 4 plus 6 is a 10. So I have 5 groups of 10 plus the 5 that I never matched with anybody, and I get 55. So what some parents don't like is that we're teaching math in schools these days where there's more than one way to find the answer, and that's great. It's not like any method works, but there is more than one way to solve the problem. And the more different ways you use, the more sure you are that you have the right answer. Now, of course, if you were to remember your formula, n times n plus 1 over 2, then if you're counting up to 10, this would be 10 times 11 divided by 2. The 2 and the 10 cancel, and you get 5 times 11, which is 55. So if you remember the formula, that's a great way to do it, but you might not remember the formula. But you can think out the problem and write it out and get the stuff going on the things that are going on there. Now, this idea of canceling actually brings up another simple thing about quantitative reasoning, and that is that some ways of getting the right answer are not right. So I need someone to tell me, if I was to ask, what is 16 over 64 in lowest terms? What fraction answers the question, what is 16 over 64 in lowest terms? Can somebody unmute themselves and shout out an answer?
1/4.
Was that 1/4?
Yes.
How did you get that?
Yes, 16 times 4 is 64, right?
Okay, so you divided 16 by 64 and got 1, and 64 by 16 and you got 4.
Yes.
Now, a student who was in your class who watched you cancel something in the numerator and something in the denominator would look at this problem and say, oh, but can't I just cancel the 6s? And if they did, they would get the same answer, but not for the right reason. I mean, it's completely, because you don't cancel digits, you cancel factors. And that's a problem that students in your teaching, sitting in the 3rd, 4th, or 5th row, could watch you do something on the board and have no real understanding of what you're doing or why you're doing it. Slashing something above the horizontal line, slashing something below the line. If you're not careful, you could end up, students think they have an algorithm that's a lot faster, and it is faster. But this is the difference between validation and verification. 1/4 can be verified to be the right answer, but it's not a valid answer because it didn't come from an algorithm that was reproducible and had a degree of certainty that's in it. So that's a little bit of what we mean by the quantitative reasoning has to be there. And one of the things that's important for parallel computing is that there are lots of ways of doing different algorithms, some of which lend themselves to long vector streams like GPUs, some of which do work better for massively parallel systems like MPI would work better. And sometimes you just have to think of a different way to do the calculation. I mean, the fast multipole method is a very different method than the brute force way of summing all the particles in an n-body system. So we'll talk about where some of those things are going. Now, as we're going through algorithmic thinking, and again, this is going to touch on some semantics. There are many, many different areas of math and science that if you step back a little bit, the math looks absolutely the same, but they're very different in what they mean and how they can be interpreted. Let me give you an example. For a lot of students, when they're doing physics, they hear the sound of F equals ma. And they just memorize that as an equation, or they use it as a formula to calculate for an unknown, but it's actually a model. Let me read this to you in English. Forces cause masses to accelerate. What F is equal to m times a? It's the force that causes the mass to accelerate that's equal to the product. Another way to look at this is that forces are proportional to the accelerations that they cause. And the constant of that proportionality is the mass. So I could measure this. I could do an experiment where I do a force observe the acceleration, I apply a force, I observe the acceleration, and I should expect to get a straight line. And the slope of that line, by coincidence, is m. Do you remember y equals mx plus b? But if you were to look at chemistry or biology, each of them have something where one quantity is equal to the product of two things. But it has a completely different meaning. The semantics are different. We don't say that temperature causes pressure to volume. In chemistry, this equal sign is not a causal statement. It's a statement of conservation of energy, that if I measure the energy of a system in terms of its temperature, and N is an amount and R is a constant that makes the units come out right, that is equal to a pressure, which is an energy density times a volume. So if I measure it this way, pressure is a force per unit area times a length times area. The areas cancel, and I'm left with a force times the length, which are the units of work. So in chemistry, the equal sign is more often than not a statement of the equality of the energy measurements on both sides of the equation, where in physics, this equal sign is a statement of causality. In biology, the equal sign is often an equation of explanation. If I have a certain number of rabbits and they're changing over time, it is because a fraction of, and the word of in mathematics is a multiply, a fraction of the rabbits are having bunnies. This is a simple birth model. A fraction of the rabbits cause a change in rabbits with respect to time, or rabbits are changing, the dr, because a fraction of the rabbits are having bunnies. So depending upon how you're dealing with the fact that you've got one quantity is the product of two things, how you get there is different. Forces cause masses to accelerate. Temperature is a measure of the energy content or the energy density. Rabbits are changing with time because rabbits are dynamically having bunnies. Now, continuing that thinking along the lines of analogy, here are 4 analogies that are used across the curriculum. And we're going to use one example from each to show you that the basics are there and are not that hard computationally if you think about it. And the 4 examples are system dynamics, which is essentially summarized by what you have is equal to what you had plus what changed. You're talking about the system. What do you have in the system? I have rabbits, I have sick people, I have money, I have a certain number of atoms, I have a certain number of people that have a disease, I have a certain number of people that don't have the disease, but what you have is equal to what you had plus what changed. And many, 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 many iterative difference equations that could be representing differential equations can be solved by this iterated linearization of what's changing in the system. So if I come back over here and I want to talk about this across the curriculum, you could do physics. You could say where you are is equal to where you were plus how far you've moved. How fast you're going is equal to how fast you were going. Sorry about that. plus the change in the velocity. The number of healthy people is equal to the number of healthy people you had before, plus the change in the number of healthy people. And if you think about this, the actual units or the semantics don't matter as much as what are you measuring in what units and over what length of time. And you often end up with difference equations, but they all will evolve iteratively into this form. So let's do the rabbit model. The change in the number of rabbits over time can be approximated as a difference equation. And we said that this is equal to some fraction of the number of rabbits. This is called the birth fraction or the birth ratio, but some of the rabbits are changing the number of rabbits over time. Now, if I multiply up by delta t, by the change in time, then I would have a fraction of the rabbits are generated in a given time scale. And these are the new rabbits minus the old rabbits is equal to b times the old rabbits times the change in time. And if I take the old rabbits and put it on the other side, then what you have is the new rabbits. What you had are the old number of rabbits, and you're adding the change in the number of rabbits. So you can put it into that form. And then you iterate, you take a time step, you take another time step, you take another time step. And as long as you understand what is the model of change, you can iterate that to integrate this model all the way up. Now I'm going to demonstrate that. You can do this along with me or just watch me do it. If you right click or control click if you're on a Mac, this particular, I'm downloading an Excel spreadsheet. And then I'm going to share this with you, I hope. Now, all I've done on this spreadsheet is on the left side, this is a system model of rabbits. And all I've done in this column is I've just typed out the text that I had on my iPad. The change in rabbits per time is a fraction of the number of rabbits. I multiply up by dt. I separate out the change as the new minus the old. And I write it in the expression that the new is the old plus the change. Now, if I have a birth fraction of a half, that means half of the rabbits generate a bunny. So if I start with 2 bunnies and a half of those have a bunny, I now have 3 bunnies. If I go one more time step, I should have 4.5 bunnies. If I add half of that, which would be 2.25, I'd have 6.75 bunnies. And if I actually go down and iterate that over and over, you get essentially exponential bunnies. Now, let me show you the formula. What we're going to cover in the spreadsheet workshop is the fact that constants no longer have to be defined as $. You can actually give this b, this 1/2, if you look in the name box, I actually call that b. And if you look at the formula, I actually call the old number of rabbits the number in this column, which is the old number of rabbits. And I call DT, DT. So it turns out that in the newer versions of Excel, you can actually use an algebraic representation that's reasonable, able to be reasoned with. This little @ sign means that you're taking it from a column. That's all that means. But you can do different models. Remember, I said that if your system model is different, it doesn't necessarily have to be proportional to the number of rabbits. You could say that the change in rabbits is at every time step, I get 100 more rabbits. What if that was the case? Not proportional to the number of rabbits, but just at every time step, I got 100 more rabbits. If I did that, let's see if I can get my. Oh, I ended up getting rid of an entire column. Let me stop this and start it up again. This happened this morning when I was doing it on Zoom. Excel on Zoom has a delay in it that can mess up your thinking there. So if I came over here, come all the way
We
down.
can't see your screen.
Oh, I didn't share it again. I'm sorry. Go back to Zoom, click share, pull up the Excel model. Okay, so what I was asserting was if the model of change is that it was not proportional to the number of rabbits, but it was just a constant number, I copy that all the way down, you would get linear rabbits. If I came up here and said that my model was that the fraction was proportional to the number of rabbits, but that itself had a carrying capacity I don't know if you can see that I've got to make this R sub 0. So now I have a carrying capacity and I'll copy that down. And I'll extend the model in time a little bit longer. Then you end up having a limiting case of things that are going on there. But in each of these cases, once you have the model, you get the model right once, and then you copy it down, just double click, and you can study different conjectures, different driving questions. What would happen if? But all of it comes down to what you have is equal to what you had plus what changed. We could do this with falling rocks in physics. We could do it with chemical reactions. We can do it with health models. We'll end up doing an SIR model and showing you. But when we go to system modeling, there's different ways to do this. Excel is simply line by line, but all you see are the numbers. You don't really see the model, and you don't really have a picture of the model. That's why people invented system dynamic software that lets you represent this as a concept map. So if I show you a concept map, I could do something fairly simple. I could come over here and say that I have a box of rabbits. And I'm going to make the box of rabbits bigger. The rabbits are changing over time. Change in rabbits per unit time. I have a variable which is a birth rate or a birth fraction. And the birth fraction affects the change because that would be the B. And I'd have to multiply that by the number of rabbits that I have. But this is what some people think is the only way to do system modeling, is these concept maps. It's a great way to do it because you see the model. I have rabbits, they interact, a fraction of them change the rabbits and they get dumped into the box of rabbits. And you get this loop that's coming on here. If you start with 2 rabbits and a birth fraction of 5, but it could be anywhere between 0 and 1. And the change in the rabbits is just a fraction of the number of rabbits. So we can read this in English. The change in rabbits is a fraction of the number of rabbits. Then if you were to run that model, and I take a look at the number of rabbits, then you get exponential bunnies. Let me limit that to what we had in the other model, where we only ran it for 30 days or 25 days. But what we'll do is we'll look at a bunch of these different models in the system dynamics class. And Excel could be one way to do it. You could also do it with a variety of pieces of what I call middleware or modelware. And you would get the exact same numbers that we had before. If we looked at it as a table, I don't know if you can see, you get 2, 3, 4.5, 6.75. It's identical, but the difference is using this software to do system dynamics thinking lets you see the model in real time. So we'll talk about that as we go on. If we go back and look at our sort of list of analogies, there are many things that are basically, I am the average of my neighbors. When we do the Excel class, we're going to do something that has to do with diffusion, and we'll show how we can use color as a numeral. We'll show how to do names of variables. We'll show how to do initiations, loops, and all of this without actually writing a program in Excel. We're just setting up relationships between the cells and then iterating it over and over and over. And you'll see how to do the averaging of the neighbor. Another analogy that we'll look at is that 2 objects interact and one object acquires a property the other already had. This is an important part of agent modeling. And I'll show you an example in a second, but let's think about it. I have a tree that's on fire next to a tree that's not on fire. The wind blows and suddenly the tree that's not on fire becomes the tree that's on fire. That's the interaction. I have a person with the virus and a person without the virus. They interact and now the person without the virus becomes the person with the virus. I have two people in an alley, one of which has a wallet, the other doesn't. They interact in some way and the person without the wallet now has a wallet. Now let's see if I can get you to be a little bit more participatory. Let's get different people chiming in. How many different models can you think of that satisfy the verbal description? A person with a wallet interacts with a person without a wallet, after which the person without the wallet now has a wallet. What would be different scenarios you can imagine? The only difference is the semantics. Who would like to unmute and give us your idea?
I can give it a shot. So one scenario would be the one person handing out his wallet voluntarily to the other person. Alternative scenario would be one person stealing another one wallet, for example.
Right. What was your first scenario? Aaron, my speaker's not.
I heard it as giving the wallet voluntarily. So one
Right.
person gives their wallet.
So it could be the first person found a wallet and he's returning it to the person that didn't have the wallet. It could be the person that has the wallet is gifting a birthday gift to the person that now has a wallet. It could be the person is selling the wallet, or the other example is they're stealing it. Yes, but the point is, at a very high level, two objects interact and one of the objects acquires a property the other one already had. Now, I want to do this showing you the simplest example of the spread of a disease that we started with this year. We did a lot of disease modeling with the pandemic. We did SI, which is susceptible infected. We did SIR, susceptible infected recovered. We did SEIR, susceptible exposed infected recovered. And we did it in both system modeling and agent modeling. And in the system modeling workshop, we'll talk about the various models that we've successfully used. In the agent modeling workshop, we'll talk about a model similar to this one. This is the simplest one. Let me tell you the advance that's been made in middleware. If you can tell a story in English, I don't know about other languages, but if you can tell the story in English and identify the nouns, the verbs, the adjectives, and the adverbs, and you can identify those parts of speech, you have already built a model. Let me read to you my story. If a healthy person is next to any sick person, with some chance, they change into a sick person. Another part of the model, a sick person after sufficient time has a chance to get better. Here's another part of the model. Healthy and sick persons move randomly in the world, but sick persons move slower. Now, if I was to run that model, we're not going to make any changes, but I'm just going to show you what that model looks like. I already built the model for the previous workshop. We're going to reuse it today. I have blue squares represent healthy people. The green square is a sick person. The red cross is just a person who in this model simply counts the number of people and makes a graph. But when you input the model into this software, which is called Agent Cubes or Agent Sheets, every rule in the model is an if-then. If that's not true, you go to the next, and that makes it an else. If that's not true, you get another else. If that's not true, you get another else. But let me read this to you in English and see if it sounds familiar. If I see that I am a healthy person next to any sick person, there's a % chance that I change into a sick person. And when I do that, I start the clock measuring how long I've been sick. If I'm not a healthy person next to a sick person, I'm still a healthy person, then I move randomly on the red squares. What about the green people? If I see that I'm a sick person, I check to see if I've been sick long enough. And if I have, with a 50% probability, I change back into a healthy person. Otherwise, if I'm not doing that, there's a 10% chance that I move. That means the sick people are moving 10% of the time that the healthy people are moving. It will appear they're moving slower. But what if you're not moving? Well, you're still sick for a longer time. And in fact, the time that you've been sick is accelerated. So if you're not moving, you get better faster. That's to simulate resting. And if you were to run this model, pay attention to the green square. I'm going to take it one step at a time. And one of the things you should notice is the green square is moving fewer times than the blue squares. And as more and more people are moving, let me run it. You'll notice, according to the graph, that the number of healthy people is coming down, the number of sick people is going up. But there's some fluctuation because some of the sick people can get better. So eventually I might reach an equilibrium situation where in this case, there's no cure. You just get better, but you're susceptible to get the virus again. We could make a different model that had a different set of rules. But the idea is, the thinking is what's in the story. What are the nouns? Person, world. What are the adjectives? Healthy person, sick person. What are the adjectives? Move slower. What are the verbs? Change, move. What are the adverbs? Move randomly. So as you're doing this, you can get a very big sense of what's going on. But the idea is, this is one way to implement an agent model. You can also write code to implement an agent model. You can also build agent models in Excel. So during the Excel workshop, we'll show you how to build different types of models in Excel, some of which could be considered system models, some of which could be considered agent models. If you take the agent modeling workshop, we'll talk about different tools that you can use to build agent models. If we do the system dynamics workshop, we'll talk about different tools that you could use to build system models. So eventually, they're sort of self-referential from one model to a different model going on there. So we'll stop this. So you can get different kinds of things that are going on there for the types of models that are going on. The two things that scientists like to do are tell stories and draw pictures. The good news is that advances in what, again, I'm calling either middleware or modelware, is that the concept map becomes the model. The story becomes the model. But none of that happens without a human being thinking through what's in the model and then simplifying it and starting it very simply. We often talk about two ways of looking at scientific models. One is like Shrek, where you say models are like ogres, are like onions. They have layers. You start with the onion and you peel back the layer and you peel back the layer and you're crying and you peel back the layer. And when you get to the very center of the onion, there's nothing there except the center of the onion. But that's one way, is you start with the model and you peel back the layers to get at the simplest beginning part. Another is, it's like a pearl, where you start with a grain of sand that's an irritant in the oyster. And that irritant is coated by the oyster with a layer of nacre to sort of make it so that it's less likely to irritate it. And it builds up layers and layers and layers till eventually you get this beautiful pearl, but you have to start somewhere and add on to it. And that's the same whether you're doing numerical modeling, system modeling, agent modeling. You have to be thinking about what's in the model. Now, before we go, I want to just do a couple of other things to show you some other modeling environments that could be thought of as being either agent or system modeling. So let me share my screen from. So the first is purely mathematical modeling. And I want to use an example where we're using the computation to consecutively, repetitively change the model and represent it, change the model and represent it, so that you can see the pattern of behaviors. And I'll start off by using the multifunction data flyer, which is one of the examples, again, from Interactivate. We'll do the simplest model we can think of, which is y equals mx plus b. We're able to parse the expression, and we know what's a constant and we know what's a variable. And there's an old joke from Notre Dame that constants aren't and variables don't. Constants aren't constant, they're parameters that you change, and variables don't vary, it's almost always x. But if I was to write out an equation that looks like y equals mx plus b, each constant becomes a parameter with its own color. And so I can change the m-ness of this function, and you can see what effect it has directly on the graph. The larger the value of m, the more steep it is. If it's 0, I get a horizontal line, and if it's negative, it's going down the other way. If I change the value of b, it turns out that if you're careful in your observation, you'll realize that b is the value where it's crossing the y-axis. But you can do so much more with a computational tool to explore a function rather than just paper and pencil. So for instance, if I leave breadcrumbs every time I change the intercept, what can you tell me? What do you see is true about lines that have the same slope but different intercepts? What do you see as the relationship between those lines?
They're parallel.
They're parallel. And what we've been able to test with middle school and high school kids is if they've used this tool, we can come back later and ask them a separate question that doesn't look the same. If I wanted to show that two lines were parallel, what would have to be true? And we got a huge increase in the number of students who could say they have to have the same slope because they've seen it, they've gotten their hands on it. You know, if you come up here and say, what if you had a times the, let me get rid of the trace. A times the exponential of minus b times the quantity x minus c, the quantity squared plus d. Let me see if I've got that right. Do you see that you get a Gaussian, that little bump there? But now you can explore the fact that what multiplies the exponential changes the height of the function. What multiplies the argument of the function makes it wider or narrower. What shifts the argument of the function moves the Gaussian left or right. And what gets added to the function moves up and down. Now, you could write a program to do this. You could write a procedure in Mathematica. You could write a series of procedures in other software environments. But you can simply take something like the multifunction data flyer and immediately plug it into your curriculum. And page 42 has an equation 17, and it's an oscillating function. And you say, well, I don't know what an oscillating function looks like. Well, you could come over here and say, oh, well, here's some things, sines or cosines. Let's pick cosine. And now you can see that the multiplier in the front changes the amplitude that amplifies it. There's a function that tells you how frequently you get another bump. That's the frequency. There's the phase that tells you where the function starts and stops. And then there's the bias, which is the average value around which the bumps are bumping. But the ability to take virtually any of these equations that students have struggled with to understand what do they do and how do they do it. My personal goal when we designed this years ago and have implemented it over and over, first in Java, now in JavaScript, is to kill off what I call the big lie in math and science education. And that is you have a graph, an equation, and the lie is it says, as you can see from the graph, if you do this, this will happen. And most of my students, and myself included, don't see that from the graph unless we can get our hands on it and play with it and see what it really does and how it does it. And it uses computation to enhance your thinking. It uses your computation to show you what you're thinking about. And that's just, again, one of these examples. I want to show you two more examples that were originally built in Fortran. Then they were translated to Java, and then Aaron and his crew have translated them to JavaScript. One of which shows you the power of computation for what's called the n-body problem. The only physics in this model is F equals ma. I don't have any of the higher order physics. This is 400 solar masses in a, try doing this with a telescope, in a spherical distribution. Let me make it a little bit bigger. Can you see that I have these stars and that they're approximately distributed? And I could randomize the stars, but in this case, they're being randomized in a spherical distribution. And I'm going to have them not rotate. So I have 400 objects suspended in space, and I let go and gravity takes over. What do you think is going to happen? Somebody want to give me a verbal description of what they're seeing happening? And I'll rotate this as we're going through here. After about 1 billion years, there's been a gravitational infall that's fairly symmetric in all directions. Then there's a slingshot effect in the middle, and then they start going out again. And this is giving essentially if I looked up the words globular cluster.
Can't see that.
Oh, that one didn't show up. Okay, let me. Are you seeing this page now?
Yep.
So what you're seeing here is globular clusters and the possibility of explaining it by saying if you had a blob of mass that had no angular momentum, then the force of gravity itself could explain how you could end up with objects that look like globular clusters. Now, if instead you gave some rotation to these objects, and I'm going to try to convince you they really are rotating by tracing them. Do you see the rotation? Now I'm going to put a box. And what do you notice about the infall perpendicular to the plane of rotation versus here? So as they're rotating around here, you can see that it maintains its radius in the perpendicular direction, but in the other direction, you're getting an infall. And you end up with the disk. And depending upon what other physics is going on, whether you have instabilities, then as you're going through here, you start getting arms and spirals in this disk sort of distribution, but you don't get a globular cluster, you get a disk-like galaxy, some of which have arms and some of them don't. But the only difference between that and a block sliding down a plane is it's F equals ma, but you're doing it for 400 times 399 other stars, and you're doing it in 3 dimensions, X, Y, and Z. So it's a massive n-body problem, but it can be understood simply by taking the pairwise forces and calculating what's happening and then summing over all possible combinations. I mean, there's other ways to do it if you're doing higher order terms like multipole methods and things like that. If instead of doing the forces, you did energies, let me see if I can show this. We're going to look for something that minimizes the energy.
We can't see it. Oh, there it is. Sorry.
So I have different types of things, and I can have different numbers of particles, and I can randomize the particle positions. And then I don't know if you can see the fact that there's an energy 783.88. If I have one repulsive particle close to another, the energy goes up. If a particle is close to the wall, the energy goes up. And the question is, what would be the minimum energy? So I can use an algorithm called simulated annealing to simulate annealing. And you start off with a gas, those large fluctuations. As the temperature is reduced, smaller and smaller fluctuations come about, and you end up with a near crystalline structure. If you go in with your scanning tunneling microscope and move particles out of the way, and then allow the system to recool, you can see that one particle finally gets back in, and you end up with the same ground state. The other thing that you can do is to take a look at the electrostatic potential. And as I mentioned before, this is an example of everybody is the average of their neighbors, and you're calculating the Laplacian, you're calculating the Laplace potential for this particle. But again, what you're doing is you're using the power of computation to enable a very simple algorithm. Take a step if the energy goes up, roll the dice and maybe accept the move. If the energy goes down, absolutely accept the move. It's called simulated annealing. It's also variational Monte Carlo. But instead of doing it for one particle, you're doing it for tens or hundreds or thousands of particles. And the computation allows you to ask driving questions and answer them with the power of dynamic, visual, and interactive modeling. So this is what we've been trying to kind of get across in these things as we're doing it. The last part of this introductory workshop across the curriculum is to talk about different resources that are available. We have 4 basic resources of resources. There's computational biology for biology educators. You can't see it because I didn't share my screen. So if you click ahead a couple of slides, you've got computational biology for biology educators, computational chemistry for chemistry educators, computational physics for physics educators. And an important part of that is the open source physics materials and the partnership to integrate computation in undergraduate physics. This is called Pickup, and they have their own set of workshops and materials that are there. And then there's an earth science library as well that allows you to look at different themes and project-based learning. So that's basically the across the curriculum pieces that'll be here. I see, what does he mean by the Laplace potential? Del squared on the wave function is 0. That's what I mean. You're calculating every point is the average of its neighbors, where you're calculating the energy at every point in a massive n by n grid, where you have charges at some points and the rest of space is blank. So what you're solving is the linearization of del squared being 0, that there's a no curvature in the potential field. The potential answers the question, if I put a test charge at that point, the test charge times the potential, times the electric field, will give you the force that's on that particular particle. So I want to bring the formal presentational part of this to a close and drive everything else from here until people want to go away with questions or comments or concerns. But I hope what I've been able to do is to show you that a few simple basic ideas and tools that have already been built could be built into your curriculum as a starting point, and that you can see that there is a role for computation in several different areas. There's a number of things that I skipped over because of time, or because when we did it a couple of weeks ago, people were not as interested in it. So I added some things and took some things away, but we can go back and show you those things too. But for now, I want to thank you all for what you've done. We're going to do 3 things before we really let you go. One is I'm going to turn it back to Aaron, who's going to tell you about other resources. We're going to talk about some books that are available, and then we're going to open it up for any kinds of questions that you have. I don't know if you want to do them in that order. So Aaron, do you want to?
Sure, that sounds great. So the things I'm going to be talking about are all linked on the Google Doc. I'm putting another link to that in the chat. So I do want to spend just a few minutes sharing some additional opportunities specifically from the XSEED project. So I'm going to share my screen here. And so the first opportunity is that we'll be hosting the online workshops we referred to earlier coming up in June. We'll cover the same topics we did today, but in much more detail. So each one of these workshops will be 2 days from 1 p.m. to 4 p.m. Eastern. It'll all be held on Zoom. The first workshop is June 15th through 16th. We'll be focusing on the modeling with spreadsheets and web resources. June 22nd, 23rd, we'll be focusing on systems modeling. And then June 29th and 30th, we'll focus on agent modeling. The intended audience for these workshops are faculty and instructors who teach courses and who are either currently incorporating computation in those courses or who are looking to do so. The workshops will have limited enrollment so that we can keep them very interactive and hands-on, and so that we can also provide stipends to participants. We'll be giving out $100 stipends per workshop per participant. Those stipends are available to participants who teach courses at any US institution. And in order to receive the stipend, you'll have to attend the entirety of both days of that workshop, complete all the activities of that workshop, and respond to surveys. Each workshop requires registration on both the Exceed user portal and the National Computational Science Institute website. And that's so that both projects can track who attended the workshops and so that both can administer surveys and collect responses. So we'd encourage you to apply to any or all of these workshops, and we'd appreciate your help promoting them to your colleagues as well. And in addition to the workshops, the education program for Exceed can work directly with you to help you integrate computation and data science into your curricula. So we can help you develop courses, concentrations, minors, and degree programs. We can give talks on your campus, which can help promote engagement with your department and buy-in from your administration. We also maintain a website that has a database of computational science education programs, resources, competencies, and events. And this is available at hpcuniversity.org. We also offer collaborative online courses where multiple institutions each host the course simultaneously to their own students. And you can contact Kate Cahill from the Ohio Supercomputing Center about any of these opportunities. And we look forward to being able to help you incorporate computation into your teaching. Exceed also offers training in technical topics related to high performance computing, data science, machine learning, and we host a regular series of online workshops that are webcast through what's called the Wide Area Classroom, which is where multiple institutions across the country can all host participants in person and provide teaching assistance in the room while the instructor broadcasts from a single host institution. So we've run this multiple times over the years and it's quite effective. There's a regular series of topics that are covered in these workshops. And this is a good opportunity for you and your colleagues and students to improve technical skills in advanced research computing. You can earn badges by participating in the events, and all the materials are available online, which includes recordings of previous events. So Exceed's primary offering to the research computing community is a collection of machines and people to help you use those machines. So these include resources for supercomputing, big data, machine learning, and cloud computing. And there are different ways to obtain access through allocations that you can apply for. So startup allocations are easy and fast to obtain, and they allow you to try out the various systems. If you get an education allocation, you can use that to provide access to your students in courses and training events. And you can also obtain allocations for your research work. All of these are available cost-free to researchers and educators at any US institution. If you're interested in engaging with undergraduate students, we run a program at Shodor called Empower, which runs each fall, spring, and summer. And the goal of this program is to engage undergraduate students in the work of Exceed through projects in computational and data science research, systems and user support, visualization, and other activities related to the types of things that Exceed staff do. We recruit both mentors and students for this program. So the mentors bring projects that the students can work on, and we provide the stipends to support students working on those projects. Mentors can either have particular students in mind, or they can leave the position open to any qualified applicants. And we have 3 levels of participation for students depending on their prior experience. And there are associated stipends for each level of participation. That includes a learner level, which doesn't assume any prior experience. And so we encourage you and your colleagues and students to apply for this opportunity. We're currently accepting applications for the fall 2021 program. Those will be due June 25th.
I just want to mention a small lament that the stipends are for the student. We don't have stipends for the faculty mentors. The benefit to the mentor is you get an interested, well-trained student to work on your project. And some of those projects have been to create curricular materials to be used in a class that you'd be teaching in the next year. But unfortunately, we don't have funding for faculty mentors, but we do have funding for students.
So Aaron, I have a question, please.
Sure.
Or shall I wait until you finish, maybe?
No, go right ahead.
Okay, it's actually a very naive question. So while I was registering to these workshops, I was asked about my status, and I am a postdoc, but you know, at the university, for example, they consider postdoc as a student. So I don't know how that will affect my application for the workshops. So I'm instructing high school students and undergraduate, and I'm trying to implement a lot of this computational thinking in my instructions in the context of the projects I am instructing them in.
Mm-hmm. Yeah, so I think Dr. Panoff can correct me if I'm wrong, but postdocs who are teaching students would be considered eligible for the workshop. Is that correct, Bob?
Sorry, I was muted. Yes, that's correct. It's obviously, you know, there's a space available. So make it very, very clear in your text in the application that you are in an instructional capacity. Other people can attend the workshop. They just may not be eligible for the stipend.
Actually, my motivation is not the stipend, it's the workshop. So what I'm saying is that I already registered as a student because there was no postdoc option clearly stated. And
Right.
I didn't, yeah, but I am instructing high school and undergraduate students.
Right, and our hope is that you'll be able to be a better teacher in the future.
Okay, thank you so much. Perhaps I'll just follow up with an email to Aaron, just to remind you that my real status is instructional postdoc as opposed to student.
Right.
Yes, absolutely.
Okay, cool.
Yeah, please feel free to reach out to me or Dr. Panoff by email about any questions like that, and
Okay,
it'd be
understood.
great
Thank you so
to
much.
have you in the workshop. Yeah, thank you.
Yes, sir.
So I've got a couple other opportunities I want to talk about through Exceed. Another one, which is actually growing out into its own organization at this point, is called the Campus Champions. This is a professional organization for professionals who facilitate research computing. So if you help researchers use computing on your own campus, you might be interested to join the Champions. They have hundreds of members, a very active mailing list, and meetings throughout the year. So this can be a great way to help support the researchers on your own campus, and for you to hear about some of the best practices and to network with other facilitators of research computing across the country. So this isn't necessarily a group for researchers, but more a group for people who are helping researchers to use computing. And it's a very active group. And then if you are interested in building up the computing resources on your own campus, maybe you want to install your own cluster computers, Exceed can help you deploy advanced research computing hardware and software at your institution. So we can provide site visits to help you set up your hardware and software. And if you're interested, make it part of the larger Exceed ecosystem. So those are all the opportunities I wanted to share with you from Exceed. I'm going to stop sharing my screen. There are a few other opportunities linked in the Google Doc for the webinar today. I know that Bob wanted to mention some of the books that we might recommend, because that was asked about the most recent time we did a webinar on this topic. Bob, did you want to talk about some of the books?
Sure. So there are several books from different authors, and the noun could be different. For instance, there's a book by Ruben Landau called A First Course in Scientific Computing, where the noun is computing, but the computing is done in such a way that you can tell how good it is. Therefore, it's scientific computing. How do you know if it's right? And it has lots of different examples and things that are going in different languages. He also has one specifically focused on physics called A Survey of Computational Physics, where again, the focus is getting physics done, but you're doing it computationally. These are examples. There's also books now in computational chemistry, biology. Angela and George Shiflett from Wofford College wrote a book called An Introduction to Computational Science, where the noun is science. And it very much follows the structure of this workshop. They had originally taken this workshop a number of years ago, went back, developed a course at Wofford, and then wrote a book around it. And a lot of the examples include numerical computing, system modeling, agent modeling, cellular automata, high performance computing. And it's a very good it's a very substantial book from Princeton University Press. And then there's a book, I don't have a copy to hold up, but it's an introduction to modeling and simulation with Python and MATLAB from Steve Gordon at the Ohio Supercomputing Center. So there are many more resources out there now than there used to be. We're trying to find a book, or if necessary, I may end up having to write it myself, on this idea of an introduction to computational thinking at the more introductory level. Most of these other books assume at some point you're going to write substantial, significant code. But I'm also interested in the on-ramp and getting people to be dynamic, visual, and interactive in the use of computing in the sciences, in mathematics, in the humanities as well.
And I did want to call out a question that Kate answered in the chat. The question was, it looks like the workshops are already full when you go to register. And Kate is correct that the wait list is not a firm limit. So even though it might say that the registration is full, there may be some people who will drop out. That happens regularly. So please go ahead, if you are interested in registering, to go ahead and register. And I think, as we said, we do need to limit the space because of the stipends, but we'll be trying to accommodate everybody if we can. And if interest is strong enough, we'll definitely be holding workshops like this in the future as well. So I think we'll continue to answer some questions that folks have. There was a question, are there any education studies as to which teaching model is quote unquote better for students? So Excel, maps, coding.
Well, I haven't written up the course that I teach at Wofford, but I use all of them, and and students gravitate to one or the other. There are certain students that are going to go into business and economics, and they love the Excel modeling because Excel is a tool they're going to be expected to use. There are people in biology, systems biology, and things that really enjoy the cutting edge where they can be developing the model and go more quickly to the coding. But remember, I've been calling the middleware because you're actually writing code. It's just a different interface. You're either drawing the picture or you're telling the story. But you really end up writing code in there. I don't know of any studies that says this is better than that. All three can address the same problems and they have different levels of understanding. So at the introductory level, we use them all for the things that people are doing. There was something that just went in and out of my brain very quickly, like a neutrino. If I think of it, I will, but you can, convince the students that, again, understanding the modeling first is more important than the programming. I mean, we're going to cover a tremendous number of programming concepts in all three workshops, and it'll look more or less like programming at some point, but most of it's going to be thinking and modeling. The analogy I use from my own youth is that when I was in third grade, they announced in Fairfax County, Virginia, they're going to start band instruction. And of course, the 6 kids in my family all wanted to be in the band. But my father insisted, because he thought it would discourage us, that we take 2 years of piano lessons before he would allow us to go into the band. And so when we did go into the band, the only thing I was learning was how to play the tuba. I already knew how to read music. I already knew what whole notes, quarter notes, half notes. I already knew how to transpose. I knew all the keys because I had taken piano lessons. And I learned on the piano, but applied that knowledge to the band instrument, which was so much easier because you're only playing one note at a time. I mean, the piano ended up being much harder than the band instrument. So we ended up with a family where everybody played a different instrument, and those in my family with curly hair ended up with music careers, and those with straight hair ended up with science or engineering careers. But we all did the music stuff. This is the same. If you learn the modeling and the thinking, when you get to programming, it's so much easier because all you're learning is the programming. You're not also learning structures and loops and initiations and assignments and operators. You've already done that. So we're going to try to cover those in the workshops themselves. But I don't know of any model. I don't know of any study that says spreadsheet is better than concept maps, which is better than an agent model. And in fact, the best students that I've had combine all three. They use Excel as kind of a sandbox to kind of get the model set up. Then they draw a picture to determine what the model is going to look like. Then they build the model in the system software. They tell their story. They build the model in the agent modeling software. And then they compare the results from all three. And some are going to learn more than others depending on the model.
So there's a couple more questions. One is, where can we find the recording of this talk? So there'll be a couple places. One is I will send a follow-up email to everyone who registered for this workshop, which will link to the recording once it's available. It's also going to be posted on the Google Doc that I've been sharing today. It will be a few days before we can post it because we need to edit the closed captions. YouTube does some automatic closed captioning, but it turns out it's not very accurate with spelling and punctuation and timing. So we'll be editing that and putting that up and sending an email out. I'll also include in that email a reminder about where to sign up for the workshops if you are interested in that. And there will also be a brief survey that I'll ask you to take for this webinar today just to tell us how you think it went and if you have any suggestions on how we can make it better the next time.
I would encourage you to sign up on the waiting list because Kate can answer this. The more we can show that there's a market for this kind of trainer, the easier it's going to be for us to assign our grant resources to offering these workshops more frequently and more often. So we have an idea of having sort of a regular series of get-togethers during the school year where we would talk about different approaches to modeling during the school year. We could also make the workshop from several weeks ago plus today available for people to go through on their own asynchronously. But the hands-on part of the workshop has turned out to be so important over the years. We're still experimenting how to do that with the Zoom. It's not as easy as shoulder surfing, walking around behind you, helping each individual faculty member in the same room. But we're going to try and we're going to measure and we're going to see how we do, and we're going to take your comments seriously, and we're going to improve the workshop and offer it again. So if you sign up, even if you don't end up in the core group of people, we're still going to try to offer this again, but this is kind of like market research. How much of a demand is there for this type of training and research? Is that true, Kate?
Yeah, definitely. Definitely any, the more interest we can show, the more we can make the case that we want to offer these more regularly. But yeah, I want to make sure that everybody who is interested has a place to attend. And yeah, so. But just keep in touch. Like Aaron said, he'll be following up with, you know, the links and the recording. So you can always ask us questions by email too.
Yeah, and I didn't prepare a slide for it, but I'll also mention that we are involved with the Association for Computing Machinery has a special interest group on high performance computing, and there's an education chapter of that. So the SIG HPC education chapter, this is another professional organization that you can join if you are interested in the education of high performance computing. And that group is kind of just sort of picking up the last few years and is getting more active members. There are workshops and webinars that are held through that group as well. It's pretty cheap to become a member, just $10 a year. And students, I think, can join for $5 a year, if I remember correctly. Yes. And as Kate mentions in the chat, you don't need to be an ACM member to join the SIG HPC education chapter. I think you also don't need to be a member of the larger SIG HPC to be part of the education chapter of SIG HPC.
Yeah, no, I've never been a member of that one.
Well, as things open up past pandemic, we're going to try to get back on the road, and we can visit schools who want to be visited and give local presentations. We can talk to student groups. We can talk to faculty groups. And Kate and I and Aaron are all good contacts for figuring out what we're going to do. There's also things that we initiate, and we'll keep you all informed on what those things are as well. But a lot of it just depends on what happens to the variants and whether the vaccines prove effective or not. So.
Yep, in a normal non-pandemic year, we'd be looking to do the workshops in person. We, each summer host workshops at local institutions who are interested in hosting us. And if you take a look back over the NICSE website, you can see all the workshops we've done. As Bob mentioned, they tend to focus on computational something for something educators. So computational biology, chemistry, physics, earth science. There was a question if attendance on this webinar is being recorded. Yes, so when you registered for the Exceed on the Exceed portal, that will be recorded. To the extent I can, I'm going to try to mark who attended and who didn't, if I can get that information out of the Zoom. And that will be in the Exceed portal. So that'll be visible to the Exceed portal admins, but the attendance list won't be public. Are there other questions or topics folks would want to review or discuss?
I just want to say thank you. That was a really great and inspiring presentation. I really enjoyed it, and I'm learning a lot. Thank you.
Good. Any other questions or comments or concerns? Okay, well, this is entirely audience-driven part of the time. So if there aren't any more questions, again, the anecdote I like to tell is when I was a Clemson University professor, my students learned to ask questions when I gave them a chance, because my response would always be, if there aren't any questions, I have some. Take out a piece of paper, put your name in the upper right-hand corner and answer the following, and then I would put up 3 quiz questions. So feigning interest was a way of defending against pop quizzes. But that what I would tell them at the beginning of the year is, I can only control whether one person in the room was going to have fun and enjoy themselves. And if that had to be me, so be it. So I enjoy doing it. So we'll have there. Any other questions or comments?
There was a question in the chat about materials before the next workshop. I'm assuming you'll share anything that people who are attending that need to know beforehand, or software or anything like that.
Yeah, it says something about next Thursday's presentation. The next workshop is several weeks, is a couple of weeks away, right?
Yeah, and it'll be on Tuesday and Wednesday. So, there's no requirement that you would have attended this webinar to attend those workshops. So
Yeah.
We're not assuming any prior knowledge or any materials to look over. There will be a pre-survey to take before the workshop, but we'll make sure to email about that. Once you register on the Exceed portal and the Nixie website, we will contact you via email to make sure that you are intending to attend the workshop, and we'll make sure you get the links to the survey plus any paperwork we'll need you to fill out for the stipend and that kind of thing. Well, it may be a good time to let folks get on to the next meeting if they have one. Thank you all very much for your attention and for being an audience today, and we hope to see you at a future event or otherwise to hear from you. Let us know if we can be of any service. Thank you.
Right. We like to say we're pathologically codependent. We want to be wanted, but we need to be needed. So if we need if you need anything, tell us and we'll try to do our best to fulfill that. Okay, bye-bye.